Welcome back. Moving on to the next video, the next example dealing with factoring. We have to find a formula in factored form that relates the number of shaded squares in these diagrams to either part A, the diagram number, or part B, the length of the base. So if you remember in previous sections, we did questions like this where we had a bunch of diagrams. There was a certain pattern with the number of shaded squares, and then we had to come up with a certain formula for the number of shaded squares. And the difference between those examples and this one is that final formula we're going to come up with, the final expression, it's going to be in factored form. And in those other examples, it was in expanded form. So that's going to be the only difference. Now, if you remember what we did, the process that we went about to get the number of shaded squares was we created tables of values and then from there tried to create a formula. So if we start with part A, we're going to relate the diagram number to the number of shaded squares. So there's a couple of different ways that you can try to go about this. So let's create a column for the diagram number. Now, what do we mean by the diagram number? Well, this is the first diagram, second diagram, third diagram, etc., etc. So we'll go 1, 2, 3. Now, to get the number of shaded squares, if you remember from those videos, we could do it in two different ways. So the first way is we can try to get the number of shaded squares directly, counting them directly. So let's do that first and see what we get. So in the first diagram, how many shaded squares are there? 1, 2, 3, 4, 5. In the second diagram, it would be 2 by 4, so 8, 9, 10, 11, 12. Then in the third diagram, we would have, 3 by 5, so that would be 15, and then we have a 2 by 3, which would be 6. So 15 plus 6 would give us 21. Now, over here, what's tough about this is a lot of times if you try to get a relationship with the number of shaded squares directly, it's sometimes tough to get that relationship. So notice from like 1 to 5 and then 2 to 12, what's the relationship here, right? It may be the difference of 4, but here there's a difference of 10. And then over here, there's a difference of 18. And then notice that these aren't going up in a linear fashion. The difference between 12 and 5 is 7, but between 21 and 12 is 9, right? So it's tough, usually, with these kinds of questions to get a relationship between whatever independent variable you're looking at. So in part A, we're looking at the diagram number, and getting the number of shaded squares directly. But if you remember, there's another way to get the number of shaded squares, and that's to go about it in an indirect way. Because the number of shaded squares, it's also equal to what? The total area, the total number of squares, right, in the whole diagram, minus the unshaded squares, right? The total number of squares minus the unshaded squares would give us the number of shaded squares. And so let's try to create expressions for this over here. So notice that this first diagram, it's what? 3 by 3. So notice that there's 9 squares in total. So what we can do is we could go 3 squared minus the unshaded squares would be 1, 2, 3, 4. Like that. Notice that all of these are squares, right? So it's always going to be the side length squared for the total number of squares. So we could put 9 here. I'm going to keep it as 3 squared. Just put in a little bit more detail to see if we can get a certain pattern more easily. And notice that 3 squared minus 4, that's what? 9 minus 4, which would give us indeed 5. What if we continue to the second diagram? What's the total going to be? Well, notice it's 4 by 4. So it's going to be 4 squared minus how many unshaded squares are there? 1, 2, 3, 4. So that's staying constant. Notice the unshaded squares staying constant in each of the diagrams. And then moving on to the third diagram, notice the total is 5 by 5. We have 5 squared minus 4, like that. And so notice that here, it's much easier to see a pattern versus over here, right? Because here, notice that the 4s, they're staying constant. And then notice that it's just going up by 1 over here each time. And so we could be pretty confident that the fourth diagram, if we were to draw a fourth diagram, continue this pattern, what would be this portion? It would be 6 squared minus 4. We would end up having a big square with 36 small squares within it. It would be 6 by 6. And then there would still be 4 unshaded squares. So the number of shaded squares would be 36 minus 4, which would give us over here 32. Okay, so again, it's easier to see a pattern here versus seeing a pattern over here. Now, what if we were to generalize it? Because that's what we have to do. So let's put in a variable here. What if we're on the nth diagram? So what's happening over here? Let's maybe, you know what? I'll erase this column just so we got less going on the whiteboard here. So notice that the first diagram number is 3 squared minus 4. The second diagram number is 4 squared minus 4. The third diagram is 5 squared minus 4. So what would the nth diagram be? Well, notice that the pattern here is that this number, this base over here, it's actually 2 more than the diagram number each time. So if we go 1 plus 2, that would give us 3. 2 plus 2 would give us 4. 3 plus 2 would give us 5. So if we're on the nth diagram, we would have n plus 2. That's going to be squared, and then this minus 4 is staying constant the whole time. Right? So one more time. The 1 and the 3, difference of 2. The 2 and the 4, difference of 2. 3 plus 2 gives us 5. So if we're on the nth diagram, it's going to be n plus 2. And that's going to be the base length, pretty much. And then we have to square it to get the total number of squares. And then we're subtracting 4. Right? And so that right there ends up being the expression. So we still have to put it in factored form and all, but that's a good start right there in terms of getting the actual general expression. So what we can do is for part A, let's, you know what, I'll erase this over here. And so for part A, what I'll do is I'll let n equal the diagram number. You could let it be x, you could put any variable. And then we'll let s equal the number of shaded squares. And so the formula that we came up with was s equals n plus 2 squared minus 4, like that. Now what we have to do is we have to give the formula in factored form. So what we got to do is we got to factor this. So a couple of ways we can do that. First off, you can notice that you're dealing with a difference of squares. So we would have minus 2 squared right there. The 4 we could change into 2 squared, and then notice you're dealing with a squared minus b squared, and we know that is equal to a minus b, a plus b. Right? So notice that the a value is n plus 2, the b value is 2. And so we'd have this would factor into a minus b, so it would be n plus 2 minus 2, a minus b, a plus b, like that. And then what does it simplify to? Notice those net out to 0, so we'd just be left with n in the bracket, and then over here we would have n plus 4. Right? So that would be the factored form. This here, it factors into n times n plus 4. And so that would actually be the final solution. And then you could test it, right? So you could take 1, plug it in for n, so we'll have 1 times 1 plus 4, which is 5. 5 times 1 would give us 5, and that was the number of shaded squares that we got. That was in that column, the number of shaded squares column. What about 2? Well, we'll have 2 plus 4, which is 6, times 2. 6 times 2 would give us 12. We had that value in that column as well. What about 3? 3 times 3 plus 4, which is 7. 7 times 3 would give us 21. Right? So we could be pretty confident that that value there is correct. And notice how tough this would be to get if we were trying to just work with that number of shaded squares column. Right? We had to go about it indirectly, doing the total minus the unshaded in order to get a fairly smooth formula like this. We first had to get this, and then we had to take this and factor it in order to get that. Another way you could factor this, because this is to the power 2, it's not too big of a deal, is you could actually expand everything. So you could go n plus 2 times n plus 2, then we could keep the minus 4. When you expand this, when you FOIL it all out, you'd end up with n squared plus 4n plus 4 minus 4. Right? You'd have 2n plus 2n, and then that would simplify to 4n. And then notice the 4's here cancel out. So you'd have n squared plus 4n, and then you could factor this. You could just take out an n, and you would still end up with that same expression. So that's another way if you want to go about it that way. But personally, when I see something like this and I'm factoring, then I usually just recognize that as a difference of squares and then factor it like that. In this case, again, it wasn't a big deal because this was like an exponent too, but maybe if you're dealing with larger exponents or maybe more complex expressions within this bracket, then I think it's better to go the difference of squares way. But whichever way you do it, that ends up being the formula for part A, relating the diagram number to the number of shaded squares. Now, what if we go to part B and we relate the length of the base to the number of shaded squares? So part B is actually, I think, going to be easier. So let's create some new columns here. So we'll go with base length. So we're not looking at the diagram number here, which is 1, 2, 3. We're looking at the base length of each of these squares. So what's the base length of the first square? It's 3. 1, 2, 3. So we would have 3. Then over here, we would have the base length is 4 for the second diagram, and then it would be 5, like that. Now again, we could do a number of shaded squares column. It would be the same thing, right? 5, 12, 21. But again, it's going to be tough to find a pattern going about it that way. So let's bring back that total minus unshaded column and go about it indirectly. So again, it was what? 3 squared minus 4, 4 squared minus 4, 5 squared minus 4. And so notice here, very easy to see the pattern because this and this are the same thing. Because remember, this is just the base length, right? This entire expression here is the area, which is just the base length squared. Well, now because we're dealing with the base length as the independent variable, it's very easy. 3 squared, 4 squared, 5 squared. We don't have to worry about adding anything to this like we did with the diagram number. And that's what I was mentioning, it's easy. And so if we have a base length of x, it's just going to end up being x squared minus 4, like that. Right? So whatever the base length is going to be, it's going to be the base length. The number of shaded squares is going to be the base length squared, the total number of squares minus the unshaded squares, which is just 4 in this case. And so from here, let's create the formula. So we'll let x equal the base length we'll let S equal the number of shaded squares. So we'll have S equals x squared minus 4. And we have to give a factored form. Notice this is a difference of squares, right? This is x squared minus 2 squared, a squared minus b squared, which would factor into a minus b, a plus b, x minus 2, x plus 2. So that ends up being the answer for part B. So a lot less algebra, again, because we don't have to worry about having like a adding or subtracting anything from this column in order to get something in this column. It's like a direct relationship. And so there's a lot less going on in the formula, so we could just factor the formula. That's a difference of squares. That factors into x minus 2, x plus 2. Right, so with these kinds of questions, take your time with them. You could even create the number of shaded squares column if you want, counting them directly. Then you can maybe notice it's going to be tough to get the relationship. So then go about it indirectly, make a column for that, and then a lot of times you'll be able to get a relationship much easier.